This is Chemical Processes for Micro and Nanofabrication. I'm Chris Mack, your professor for this class, and this is Lecture 51. On lithography, we're going to be talking about chemically amplified resist, part one of a two-part series on that topic. Last time, in the last two lectures, in fact, we spent some time talking about conventional resists, G-line and I-line style resists, for example, the DNQ Novolac series or style of photoresists. In those resists, exposure generates a product that directly changes the solubility of the resist. Remember, DNQ is converted to a carboxylic acid upon exposure. The DNQ acts as an inhibitor to the dissolution of the Novolac resin, and the carboxylic acid acts as an enhancement to the dissolution of the Novolac resin. For chemically amplified resists, or CARs, CARs, that are used at 248 nanometer and 193 nanometer exposures, the mechanism for solubility change is quite different. First of all, exposure generates an acid, kind of like for a DNQ resist, but the acid does not directly affect the solubility of the photoresist. Instead, the acid acts as a catalyst for a second chemical reaction that occurs during the post-exposure bake, or PEB. We call this catalysis reaction acid amplification. And that's why we get the name of a chemically amplified resist. And it's the amplification reaction that changes the solubility of the polymer resin in the photoresist. There are some very important effects of acid diffusion and acid loss that we're going to talk about in part two of this two-part series. Today we're going to focus on the main catalysis reaction and its implications. Let's start with exposure, though, because the exposure is the easy part. The exposure of our sensitizer is a standard first-order reaction. We call our sensitizer a photoacid generator because of the fact that the acid that we generate upon exposure is going to be the key component here. It's really no different than a sensitizer or a pack. We just give it a different name. So I'll try to use the word sensitizer to generically represent any of the sensitizer materials that we use in our photoresist, but specifically for chemically amplified resist, we use the term PAG, photoacid generator. Here's an example PAG, a triphenyl sulfonium salt. So these pH, that's shorthand notation for a phenyl group, an OH with a benzene ring that's attached at 3 places, and it's a salt, and when we expose it, this thing breaks up and generates an acid. Here I show trifluoroacetic acid. Now, real PAGs are more complicated than this a little bit, and the acids that are generated are a little bit bigger. Triflic acid is a common example of an acid that gets generated upon exposure of one of these PAGs. But I'll use this simplified acid to show you a point here. Carboxylic acids tend to be weak acids. Think about acetic acid. And DNQ resists generate very weak acids in their carboxylic acid. But this acid is not weak, it is strong. The electron withdrawing properties of fluorine tend to grab up all the electron density and pull them over to the fluorines. So over here in this carboxylic acid group, there's not much electron density left to hold the hydrogen in place. As a result, the hydrogen can very easily fly off. And that's what makes it a strong acid. Easily removed hydrogen means you have a strong acid. And this acid is actually much stronger than hydrochloric acid, for example. But it's not particularly dangerous because it's in the solid state, not in the liquid state. But the strength of the acid is important because this hydrogen is going to prove to be important in the next series of reactions during the amplification step. So we give the letter G to represent our PAG in this case, but other than that, the reaction is standard, simple, first order. And if the intensity of light is constant with time, I can integrate that equation just as we did before to get this exponential. Notice that we have the same rate constant C that we talked about before. We have the I times T, or the exposure dose, as we spoke about before. But we're more interested in the acid concentration rather than the PAG concentration. So we'll generally express things in terms of the acid concentration H, which is, by the stoichiometry, the initial concentration of PAG minus the concentration of PAG at any point in time. And so you see that the acid goes as 1 minus this exponential e to the minus CIT. Should be all very familiar. We've changed the letters that we use, but other than that, it is standard first order exposure kinetics. We have made the assumption that intensity is constant, and we saw that that was problematic for DNQ resists because those photoresists bleach upon exposure. Well, we're going to use chemically amplified resists at 248 and 193, and these resists do not bleach. They have A values of 0. As a result, the assumption that intensity is constant through the entire exposure process is a very good one, and these equations, in fact, are quite accurate, unlike the D and Q equations. All right, we've generated acid upon exposure, but that is not enough to cause our photoresist to change. Instead, there's going to be a second reaction that occurs during the post-exposure bake, or PEB. And to understand this reaction, I'm going to start with the product. The product of the reaction is over here, polyhydroxystyrene. This is our polymer resin after the reaction has been completed, and let's just think about what would happen with this material in our developer. We're going to use the same aqueous-based developer that we use for our DNQ Novolac resists. And this polyhydroxystyrene, PHS, or sometimes called P-host, is in fact extremely soluble in that aqueous-based developer. The OH group here is acidic, and it's not quite the same as a Novolac, but it's a similar phenol group that makes the polymer soluble in the developer. So this is what we get at the end of the reaction. If the reaction goes to completion, we get polyhydroxystyrene, and it's highly, highly soluble in our developer. If we want to make a resist that is not soluble in developer, what do we have to do? Well, we have to block the OH group. The OH group is what causes this polymer to become soluble. So if I want to reduce the solubility of this polymer, and you see it's a repeating chain of N in length, I'm going to block the OH group. What do I block it with? Well, we block it with a blocking group or a protecting group. We use these terms interchangeably, blocked or protected polymer. Here's a very simple early protecting group, TBOC, tert butoxycarbonyl. This is the blocking group that was used in the very first chemically amplified resists, invented by Grant Wilson, Hiroshi Ito, and Jean Frichet at IBM. Grant Wilson, now a professor, and for maybe 20 years now, a professor at the University of Texas at Austin, where I also teach, and I'm proud to include him in my list of friends. The development, the invention of this resist is one of the great accomplishments in the history of lithography for the semiconductor industry because these materials are so extremely important. Grant Wilson was working at IBM at the time of the invention of this resist. Hiroshi Ito was a postdoc working for Dr. Wilson, and Jean Frichet, a professor, can't remember what university he was from at the time, working as a collaborator. So, back to the blocking. So we need to block this OH group with something, and this TBOC blocking agent can do that. You can see it reacts with the oxygen instead of the hydrogen, and this blocking group renders the polymer insoluble. If I have, say, a 20 long chain of polyhydroxystyrene, I may block 20 or 30% of these OH groups, and that's going to be, or maybe 40%, and that's going to be enough to render this polymer very, very insoluble in the developer. All right, blocked polymer insoluble, deblocked polymer soluble. So what do I have to do? I have to somehow cause a de-blocking reaction, also called a de-protection reaction. That's where the acid comes in. We generate acid upon exposure. Here I show the ionized H+ from that acid. If I heat up the wafer, this acid will attack right here and cause a reaction, release this blocking group. Sometimes as volatile components, sometimes not so volatile, but the deblocking will result in the generation of an OH, and that makes the resistance soluble. Now, there's one important key idea here, though, that I haven't mentioned yet. The acid acts as a catalyst. So the acid comes, reacts, causes the deblocking, and the acid is generated again at the end. As a result, the acid is not consumed in this reaction. And one acid can then move on and cause a second deblocking reaction. And then move on and cause a third deblocking reaction. The acid's a catalyst. And as a result, one acid generated by one photon can cause multiple deblocking reactions, multiple events, chemical events, that change the solubility of the photoresist. It is for this reason we call this an amplification reaction, because the chemistry is amplifying the impact of the photons. One photon generates one acid, at most one acid, but one acid can generate a large number of deprotection events. So let's look at the kinetics of amplification. We have, I'll let M represent the blocked site concentration. Now you might notice I'm using the same letter M as I used for the DNQ concentration before. Why is that? Well, M is going to be the inhibitor concentration, the thing that stops development. So before I called the inhibitor the DNQ, all right, and we exposed it directly. But now the inhibitor concentration for the chemically amplified resist is the concentration of the block sites, or the protected sites on the polymer. So I want to know how fast does M disappear with bake time. So I put a little subscript to PEB on the time to make sure I'm recalling that it's the bake time and not the exposure time I'm dealing with here. And I want to know how fast do my block sites, my inhibitor concentration, disappear during the bake. Well, it will be first order in the concentration of block sites and first order in the concentration of acid. In other words, one acid reacts with one block site to cause that block site to disappear or become deblocked. That is my kinetic equation, has a rate constant K4. If H is locally constant, then I can simply integrate, and I get this exponential. What does that mean, H is locally constant? Well, that means the concentration of acid is not changing. Well, that might be true. This, after all, is a catalysis reaction. The acid is not being consumed during the reaction. So it makes sense to think of H as being constant. We'll find out in the second part of this two-part lecture series on chemically amplified resist that this is not a good approximation in general, but we're going to use it anyways to come up with a simple answer and a simple framework for thinking about how chemically amplified resists work. So if H is constant, we integrate, and we see that the number of block sites will go down exponentially, e to the minus rate constant K4 times H times the bake time. In general, it will be useful to normalize our concentrations to their initial values. For the case of the acid, I'll come up with a relative acid concentration, which is the amount of acid relative to the initial amount of PAG in the photoresist. And then I'll have a relative inhibitor concentration, which is the initial concentration of block sites being divided into the final concentration of block sites. And then we can look at our two reactions. First, exposure, and the relative amount of acid generated is 1 minus e to the minus CIT. IT is the dose, C is the rate constant. So if I add more dose, I react and generate more acid. Acid starts at 0 and eventually goes to 1 with an infinite amount of dose. Then I will get amount of block sites remaining as e to the minus alpha times h. H is the relative acid concentration, and alpha sub f is something I call the amplification factor. And I'll do two things. First of all, I'll normalize the rate constant K4 because I'm using all normalized concentrations here, I'll normalize it by multiplying by G0, the initial concentration of PAG, and that rate constant I'll call K-amp, or normalized rate constant. Then I'll say the amplification factor, alpha sub f, is simply K-amp times the bake time. Now, what do these two coupled equations tell us? First, I have dose that generates acid. And then I have amplification that turns the acid into amounts of deblocking. The amplification factor can be higher or lower depending on the time and temperature of the bake. If I increase the time or the temperature of the bake, I get more amplification. That means if I have a larger value of alpha sub f, I can get by with a lower amount of acid to get the same effect, the same amount of chemistry to occur. Smaller amount of acid requires a smaller amount of exposure dose. We'll see that then there is a trade-off between the exposure dose and the thermal dose. But before I do that, let me be a little bit more clear about what I mean by the thermal dose. There are two ways in which the amplification factor can be increased. First of all, it varies linearly with bake time. So if I bake for longer, I have a larger amplification factor. But it also varies exponentially with temperature through the Arrhenius equation. So if T is the temperature in absolute Kelvin scale, then the amplification rate constant varies exponentially with 1 over T using an activation energy, E sub A, and an Arrhenius coefficient, A sub R. Very standard Arrhenius behavior like we've seen many times before. So if I either increase the bake time or increase the bake temperature, I end up with a larger amplification factor. This is what I mean by thermal dose. I can increase the thermal dose and get a larger alpha sub f. That allows me to live with a smaller exposure dose. And in fact, if I do some calculations of how much exposure dose and how much thermal dose is required to produce a certain feature size. So here I show contours of constant feature size of the final printed image. Feature size, of course, the most common acronym in the world of lithography, CD, which is not a certificate of deposit, and it's not a compact disc. It is a critical dimension in lithography. So the CD varies as a function of these parameters, but there is this dark black line that I've pointed to, a trade-off between exposure dose and thermal dose to produce the proper CD. So here I have PEB temperature. Higher PEB temperature means I have higher amplification factor, more thermal dose. If I have more thermal dose, that means I can live with a lower exposure dose. If I go to lower temperatures, I need to use a higher exposure dose to get the same result. Higher temperature, I can use a lower exposure dose to get the same result. This is a trade-off between the photon dose, or the exposure dose, and the optical exposure dose, and the thermal dose. And this is a very important trade-off that we have in the fab, because I can easily change the PEB temperature, and I like low exposure doses. Low exposure doses mean low exposure times. Low exposure times means high throughput through the exposure system until I get to a certain dose where I can't move the stage fast enough to take advantage of that low dose. But until I hit that minimum dose level, I can benefit from using lower and lower doses. And it seems like this is a beautiful trade-off, because baking at a higher temperature doesn't really cost me anything. Baking at 135 versus 125, pretty much the exact same cost. Hot plates are cheap, and 10 degrees centigrade is pretty cheap. So, seems like this is a no-brainer. Well, not quite. We're going to find out that there can be some detrimental effects of baking at these high temperatures compared to the lower temperatures. So this trade-off is not necessarily as obvious until we take into account some of the other phenomena that we're going to talk about in part 2 of the lecture. So, lecture 51, what have we learned? You should be able to quickly and easily answer these questions. If not, please go back and review the material. First, how are chemically amplified resists different from the conventional G-line and I-line style resists we talked about before? What acts as the catalyst for the PEB amplification reaction? Why are these resist systems called chemically amplified? What does that phrase mean? And what are the two types of dose used to affect change in a chemically amplified resist? Well, in our next lecture, we'll finish up our discussion of chemically amplified resists by speaking about acid loss and acid diffusion. Till then.